Okay, thank you for coming to this presentation. We're going to talk about symmetry reduction for SumOfSquares. This is a joint work with Tillman Vassar. Okay, so we want to find a SumOfSquares decomposition of a polynomial. What does it mean? So we want to know basically if this polynomial is non-negative, for instance. And if you find that this polynomial is in fact the sum of these two squares, it's quite obvious it's non-negative. But it turns out you can find this sum of squares in an automated way by finding a PSD matrix. And so you see the link by looking at Cholesky decomposition. If you have this PSD matrix, you take the Cholesky, you actually get the small squares, and you can also go the other way. So this, the existence of this PSD matrix is in fact equivalent to the existence of this small square decomposition. And so in fact, this is a semi-definite program. So a semi-definite program is something like this. You can think of this scalar product as the trace of the product AIQ, and here the trace CQ. And the AI are in fact related to this matrix. So we want basically to find a Q such that we have this equality where X contains some monomials. So in this case, it was the monomial X cube X squared X. And so if you want this equality, it means that basically the scalar product of Q with this matrix should be equal to the polynomials. And so when in this matrix you have the same monomials, it means that you have some freedom in Q. So here you have, for instance, that this coefficient of x4 minus 2 should be equal to this matrix times Q. So it's the sum of these two entries. So you can somehow move in this subspace. Okay, so once you have this SDP program, then you can use SDP solver. There are many different sorts, but somehow this SDP program, of course, they solve better if you have smaller SDP constraints. And so you can see this by looking at the dimension of this. So Q will be in general block diagonal, and what matters is the dimension of the blocks. Because if you have many smaller blocks, it's better than having one large blocks, because the number of unknown entries in Q, it's quadratic in the size of the blocks, of course. And so here the dimension of Q will depend on here the number of monomials of degree 3, and the number of AI will depend, as you see, on the number of monomials of degree 6. So that's how you get these numbers. And so in this talk, we will try to, once you have a large SDP, to try to decompose it to smaller subblocks, so that whatever is the method you actually use, it will be more efficient because you have less unknowns and so on. And so the core of the idea is to use the Schur lemma. So what the Schur lemma says, so first I need to take two definitions. So given the finite set of matrices rho I, we say that it's reducible if there is no invariant subspace that is invariant under any of the matrix of this set of matrices. And we given two finite set of matrices rho 1 and rho 2, we'll say that they are equivalent if basically they are the same under some linear transformation. So here is two results. First, if you have two lists of matrices that are irreducible and inequivalent, then if you have that the Q matrix commutes with this block diagonal matrix, it actually means that Q is diagonal, and in fact, all the first entries of the diagonal are equal, and all the rest of the entries are also equal. So if you actually have this, it means your SDP, you can actually solve it as an LP because you're just looking for two positive numbers, not SDP anymore. And if instead you know that it commutes with also a block diagonal matrix, but the two blocks are in fact the same, what you can say instead is, so not your matrix is not diagonal, it's something like this. So you have diagonal here, 4 diagonal matrices and 4 different entries. And then you also know that Q is PSD, but it's not clear what it means for Q to be PSD in terms of this C11, C12, C12, C22. But what you can do is that you can permute the rows and columns of Q into this form. And here what you have is you have a diagonal matrix with D copies of C. And so here, if you say this is PSD, it just means that C is PSD. And so it means that you have reduced your SDP into a simple SDP or a PSD constraint of 2 by 2. So in general, what happens is that if you have M copies of row I, what you will have is that Q will be D copies of C, which is M by M. So notice that this is reversed. So if you have many copies of some small row I, you will have a few copies of some big C. So what you prefer is to have few copies of big row I so that you have a small C. Okay, so note this inversion, we'll come back to it later. So how can you be in the case that the solution Q is invariant under some action of some row I matrices? So we'll study the case where it happens because your program is invariant and it is convex. So SDPs are convex. And in general, any convex program, if it's invariant, you can restrict the search to invariant solution. So you don't know that all the optimal solution and feasible solution are invariant, but you know that if there is an optimal solution, it is there is one optimal solution that is invariant. So by looking at invariant solution, you don't lose anything basically. So what do you mean by an invariant SDP? We mean that there is some list of matrices row I such that if Q is feasible, then this matrix is also feasible and that's the same cost. So what does it mean for the constraint matrix AI and the cost matrix C? It means that for any row I, you have this relation and this relation. So if this SDP comes from a SumOfSquares program, what happens is that you have, suppose that the polynomial for which you're looking for a SumOfSquares decomposition is invariant under the action of some functions. You have some function GI that acts on your variables. And what's happening is that if you take the mapping of this variable with GI, the polynomial doesn't change. And so consider the matrices row I, such that if you look at the vector of monomials X, for which the variables are marked by GI, if this is row I X, so row I is this linear mapping, then you have that the SDP will have this invariance. And so at the end of the day, what you know is that Q is symmetric with this row I under this operation. So this is not really the commuting that we had here. So what you will need to go to this commuting relation and use the Schur lemma is you need row I to be actually orthogonal. I mean orthonormal, but in fact you can kind of play around so that you are in this case. But we won't go into detail about this. What we will detail now is if you know that you have this relation with this row I that comes from this GI, how do you do so that these row I are block diagonal? In general, they are not block diagonal, but what we will do is we'll try to find some linear transformation of the space. So you do some linear transformation on Q and the row I, such that the row I becomes block diagonal, and then you will need to use the Schur lemma to find that Q is block diagonal as well, and then you will be able to reduce. But how can you do that? We will see that next.
Okay, so before I tell you how to block diagonalize all of this matrix row I need to introduce a little bit of notation. Some of you might know the definition of group from the first abstract algebra course, but here's a quick recap. A group is just a set closed under the multiplication. So if you multiply two elements from the set, you end up inside the set together with the existence of unique inverse elements. So these are inverse elements that bring you back to the identity. So a very simple example that will be used throughout the talk is the permutation group. Which is a set of all bijections on the set from 1 to n, and the multiplication inside this composition of bijections. And of course, with every bijection, there is an inverse bijection attached to it. And if you compose two bijections, we end up again as a bijection. Here is a simple example. S2 is the set of bijections of the set of two elements. Here I use the cyclic notation, namely the first element consists of two cycles, of one that takes to 1 and 2 that takes it to 2. So that's a trivial identity bijection. And here is a second non-trivial element in this group, namely the element that takes 1 to 2, and 2 takes back to 1. So that's a cycle notation here, 1, 2. So we can say that this group acts, and this is a very important notion for groups. They act on objects, and this group acts on the polynomial ring by sending, and here the identity, of course, it sends everywhere everything to itself. But the 1, 2 non-trivial group element actually sends x to minus x. And here, when I say that this acts on a polynomial ring, that means that I take this action and I extend it to the whole polynomial ring. So not only every variable is sent to its minus, but also every polynomial with appropriate variables it sends to the induced thing. So for example, this polynomial x to the 6 minus 2x to the 4 plus 2x squared, this polynomial is invariant under this action, because we can see that all exponents are positive, even. So that means that they are going to kill this minus that we add. But if you look at its sum of squares decomposition, so it's x squared plus x minus x cubed squared, we see that neither x nor x minus x to the cube are invariant under this action. So when you hear about group actions and invariance in the previous slide, you may think, okay, if I'm looking for an invariant sum of squares decomposition, I just want all summands to be pretty much invariant. But as you can see here, it's not the case. So as you could see, this symmetric group of order 2 has two types of actions. One type is to keep everything fixed. The identity has this property. And the other type is to flip things. So that was the other thing. That was the other element in the group. And in general, all finite groups has finite number of types of action. And it turns out this polynomial ring, for example, under the action of such a group can be decomposed into irreducible subspaces or invariant subspaces. So here, the V1 to Vk are different types of actions. And furthermore, each type, V1 and up to Vk, further decomposes as direct sum of further irreducible components Vi prime. Here, this Mi is the multiplicity of the action type of your group on V. And what we are looking into is some universal projections that live into group ring that will give us the sum, the composition into blocks. So these are the projections that project into one particular block defined by the action. So here's an example for S2. The projection 1 is given by the following formula. So it's 1/2 the identity plus the non-trivial element. And you can think of this as a formal sum with coefficients or a non-commutative polynomial, if you like. So this projection, no matter what is the representation, so no matter what is the action and the space V that is acting, this projection, when we evaluate this in the action, is going to always give us projections to the invariant subspace. Whereas the pi2, which differs from the previous one only by this minus in the middle, is going to give us projection to all things that are flipped. And this may also mean that they are flipped under the minus sign, or they are just permuted when we permute variables.
So now we look into a few examples to show how this all works. So first, in this example, we have the permutation group. Okay, let's start again. Okay, so now we go through 3 examples to see how this all works. So the first example is a subgroup of the permutation groups that we define like this. So we have again the cyclic representation of the element, which is this element is 1 is mapped to 2, 2 is mapped to 3, 3 is mapped to 4, and 4 is mapped to 1. So in fact, the group generated by this element is the cyclic group of order 4. And here we can decide how this group acts on the monomial of our basis. And here the action we choose is variable permutation, which means that each permutation acts on a monomial by just permuting the variables. So here, x1 is mapped to x2 and so on. And so this polynomial, in fact, you can see that it's invariant under any permutation, but we will just study what happens if we exploit the fact that it's invariant under cyclic permutation. So SymbolicWedderburn, we detail what this is. It can compute these V1, these different types. Okay, so here, if you try the different types with the basis of all monomials up to degree 1 here, you get these 3 types. So these first types is the trivial types, where in fact every polynomial is mapped to itself by this, and then you have two other different types. And in fact, they further decompose. So this one further decomposes into 2 irreducible components, and this one, in fact, it further decomposes into 2 irreducible components if you consider the complex numbers, but with the real numbers, it's only 1. And this one is just 1. And so what you can see here is that, so this one is multiplicity 1 degree 2 in the real, and this one multiplicity 2 degree 1. So here, we actually try it with the actual SumOfSquares program. So we can see that with the show lemma, what we can say is that here you at multiplicity 2 degree 1. So the Q is, you have only 1, but 2 by 2. And here, because you had multiplicity 1 degree 2, okay, is reversed for the PSD, as we saw with the show lemma, and you have 2 PSD of degree 1, 1 by 1. And so, in fact, you can even see that at the beginning it was a 5 by 5 PSD, but now, because it's only 2 by 2 and 1 by 1, this is a second order code program, because this can be written into a second order code. This is just linear. And so you can actually use ECOS, which does not support PSD, and actually solve this SumOfSquares program. Now, a second example, this is kind of the running example of this talk, with this polynomial and the action. So here we use the group generated by this permutation, so with the 2 elements as we saw, and the action on monomials will be the sign of the permutation. So this one will be sign -1, and the trivial one will be sign 1 to the power of the degree of the monomial. So depending on whether it's even or not, we get -1 or not. So if you do that, you get again always the trivial type, and then this other type where they are mapped to minus themselves. And in this case, each type is further decomposed into 2 subblocks. And so because the multiplicity is 2 for each type, we will decompose into 2 by 2. This next example is a bit more involved. We won't use the symmetry group. We will define a new group. I will explain how in the next slide. So this polynomial is invariant under some action of this new group. We'll detail later. And then we have 4 different types. And what's happening is that here in this, for this type, you have degree 2 and multiplicity 3. So this further decomposes into 3 irreducible components, and this is even in the complex case. It's and in fact, the reason that in this time we have something that decomposes further even in the complex case is because this group is non-commutative. So in fact, in this case, the non-commutativity is a good thing. It will make further decomposition. It will allow further decomposition of the PSD constraints.
Okay, and by now you can start wondering, how much do I need to implement to make this dihedral action work with our tools? So here are a few examples. So first of all, you need to implement a dihedral group that is compliant with the groupscore.jl API. Groupscore.jl is a tiny package that defines abstract group API. It consists of about 10 methods. And it also contains conformance tests to make sure that your implementation is correct. So this API consists of 2 objects. One is the dihedral group object that is a subtype of group. This is something called parent object for group elements. And then there is a dihedral element, which is a subtype of group element. And then you need to implement group action in the SymbolicWedderburn by overloading this one method. So action of under the dihedral action of the dihedral element on an abstract monomial. Here, this abstract monomial is an element in the basis that we want to act on. If the action is not given by permutations, but by linear transformation, there is a bit more to implement on this side, but let's not go there. So behind the scene, what is happening? First of all, because these universal projections are related to group characters, we need to compute the character table of a group. This is done using rational ints, because symbolic in the name SymbolicWedderburn refers to the fact that all computations are, well, symbolic. Of course, if your group is too large, you would need to step up to rational big integers, because we are going to overflow. And then, given an action on variables, as we could observe before, we actually induce the action. So we extend this action to the whole monomials, monomial basis. And then finally, we evaluate these projections, these universal projections under this action to obtain matrix representatives. And these gives us isomorphisms to the particular blocks in this block diagonal decomposition. And finally, we decompose blocks which consist of several identical elements, several isotypical representations into further irreducible blocks, but at this moment this is numerical only. So we have seen a lot of examples, and here's another one, which is a real-life large-scale example. So this comes from my paper with Piotr Nowak and Narutaka Ozawa. This is a problem in geometric group theory, which was reduced to a semi-definite program with one single constraint of 4,600 in size. It consists also of 11 million of constraints. And then we realized that this problem is symmetric under the group S2 Reef product S5, which is a group of 3,800 elements. And after this procedure that we described, block diagonalization, we arrived at an equivalence problem that has 29 semi-definite blocks. The largest one is 58 by 58, and only 13,000 variables in total. Moreover, the number of constraints was reduced to slightly more than 7,000 elements. What is most important here is that while the original problem, 4,600 times 4,600, is not solvable under any numerical solver, this one, the symmetrized one, was solvable to a very high accuracy. We solved it up to accuracy on 1e to -10. So here is a picture of this block diagonalized SDEP constraint, and you can see that this largest block, 58 by 58, sits here. So you might think that we reduce this gray-blue grayish-green constraints to this series of small blocks on the diagonal. But the actual picture, to put this into perspective, is as follows. The original constraint is this blue-gray large square. And then we reduce this to a small square in the upper left corner. And then further, we reduce to these colorful dots that signify the semi-definite blocks inside.